All right, how's everybody doing today? Feeling pretty good? Oh crap! Man, thing one on my list is return the test, but I left them upstairs.
Can we all go on a field trip?
Yeah, I mean, if everybody wants to follow me up to my office after the
race.
Yeah, sure.
No, after.
Yeah, if everybody wants to follow me up to my office after class, I can return the test, or I'll bring them on Friday.
If I follow you up to your office, will you have it?
Yeah. It's on my desk. It's right next to my other stack of stuff. It's finished. It just is upstairs. So that was on my plan. So anyway, I'm not returning that today. So okay, there was a reading which several of you got to. I have several questions that I'm going to go over from the reading, which I've been doing a bad job of going over the reading questions. I'm sorry about that, but it's part of my plan is to go over reading questions. Okay, so the first question is, how does the death and evolution of high or low mass stars affect the birth of stars that come after it? Which is the reason that I make you guys ask questions is because you guys ask real bangers sometimes. So that's a really great question. Also, that's a question that might show up on the final because it's such a good question. How does the death of this generation of stars affect the birth of the next generation of stars? Well, so okay, what does a star do? Let's start with the beginning of the universe. So let's say the beginning of the universe, which you haven't really talked about, is made out of just hydrogen and helium. There's some lithium, but we don't care about the lithium. We don't really care about the helium either. We start with this universe that's just hydrogen, which doesn't have any stuff in it. And hydrogen is really bad at getting cold because it doesn't have a lot of lines. Metals have a lot of lines because they have a lot of atomic transitions. So if I have a metal, it can cool very effectively because as I heat the metal up, there's lots and lots of ways for that heat to get out. But hydrogen's really bad at that. So when I form the first batch of stars, the temperature's very high. And as I'll show you next week, the stars are very massive, but they're just made out of hydrogen. So they burn some helium, and then they go through this complex dance that we talked about last week, just before the midterm, which I'll recap again today, and you talked about on the homework. Then they blow all that crap back into the universe, and that crap contains metal now. And what can metal do? It can cool. So what can the gas do? It gets colder, so then you get smaller stars on subsequent generations. So I'll talk about star formation as a process, but the fact that stars are born out of the ashes of their parents is an important thing, and it changes the metal in the star. So when I measure the metallicity of a star, that doesn't have anything to do with the star's evolution. Okay, mostly doesn't. It has to do with the field that it was born from. So it's all the corpses of its parents that get incorporated into the star that determine the actual metal content of the star. So it's a very good question. That may show up. Several of you had asked for the derivation of the Schoenberg-Chandrasekhar limit, which I'm not going to go through because it's hairy and there's not anything at the bottom of the hair that I really care about. I might change my story. I need to rethink about that one. Let's see. What does a star look like at the end of its evolution? Another outstanding question that may show up on the next test. So, we'll talk about stellar endpoints today and on Friday. But the basic story is it depends on the mass of the star, and little stars wind up as white dwarfs. And bigger stars wind up as either neutron stars or black holes. Some get really big and blow themselves apart entirely and leave no remnant at all, but I don't know if those actually exist, but it's possible. So once you get a star that's so big that the photons just turn into electrons, then you blow the whole thing apart and there's nothing left. So depending on the monster, the endpoint changes. So that will show up again. Is the helium core heavier than the hydrogen core it came from? Yes. So even though we're used to helium being a lighter gas, it's heavier than hydrogen because it's more massive. In the thermal pulsation AGB stars, where does the hydrogen come from to ignite the hydrogen shell? So I'll go over this. I'm going to blow through late stage evolution again a little bit later today. But the basic idea of late stage stellar evolution is the relationship between temperature, chemical content, and opacity. So this is the fuel. This is the go. If there's not enough go, you can't do any burning. And this is how it can cool. So the opacity is an important part of this late stage evolution, because as the temperature changes, the temperature goes through really major changes as the fuel changes. So the fuel changes, so the temperature changes, so the opacity changes. These things all change in concert. When you run out of fuel, the temperature will drop, it will shrink, the opacity will go up, which means then it can't get rid of heat as much. So these are the three main things that change the luminosity and the radius, and also the temperature of the star. So the radius and the luminosity of the star are a result of the other three. So you can think about this complicated dance as fuel running out, things adjusting, then things adjusting to that adjustment. So as the fuel runs out, then it gets smaller, then it gets hotter, then it can bore more fuel, then it gets more opaque, then it starts to convect and move the stuff around. So this is kind of a complicated dance. I'll come back to it in a little bit. But the hydrogen shell, the hydrogen comes from upper shells that gets mixed down by the convection. We'll talk about that a little bit more. What is the most common stellar endpoint? That's another killer question for the test. That might be all that there is. What is the most common stellar endpoint? Well, what's the most common star? We haven't talked about that too much yet.
The smallest star.
So the smallest stars, so the stellar mass distribution peaks.
Medium.
Medium. Actually small. The stellar mass distribution peaks about a half a solar mass. So,
So M?
what's that?
That's an A star, no?
It's a K star. It's small. Right, they're little stars. So given most of the stars, given the most common star that you can have, what kind of supernova has that experienced? Is another trick question that I haven't really gotten to yet.
Wait, what did you say?
No.
No. Most stars have not blown up because most stars are smaller than 0.8 solar masses.
No, there's 8 solar masses.
0.8 solar masses. Above 0.8 solar masses, stars have exploded. Below 0.8 solar masses, every star is still on the main sequence because no star smaller than 0.8 solar masses has ever blown up. So we have to consider what's the biggest star that has blown up. What's the typical star that has blown up? So it's a very interesting question. But again, the small ones make white dwarfs, and there's a lot more small ones. So the real answer is going to be white dwarf. Let's see. I didn't understand the mass fraction graph. That's okay, I didn't spend any time on it. So there's this graph that's this real rat's nest of lines. And that's useful if you really want to understand the interior dynamics of a star, but we're not getting that far down the rabbit hole this semester. Okay. So what I'm going to talk about today, so last time I talked about the late evolution of both a 1 solar mass and a 5 solar mass star. And I'm going to go back and pick that evolution up again at the end of class, but right now what I'm going to talk about is the actual end. So, you ready, sir? So, we have this complex dance for small stars where, so we take our HR diagram. We have our main sequence here. So the stars start here, and then they lose their fuel, so they start to contract, and then shell burning starts, and then Helmholtz contraction really starts, and then the helium burning starts, and then the helium burning stops, and then the helium shell burning starts, and then you get all this wiggly crap because of the opacity. The opacity makes things oscillate. When things get up here, you wind up in this heavily unstable phase. So they oscillate a lot. And this is because of the relationship between the opacity and the temperature and the radius. So as things shrink, they get cool. As things get cooler, they shrink, and the opacity goes up. The density goes up and the temperature goes down, both of which makes the opacity go up. And then they get hotter, and then they can do stuff when they're hotter, and then they get bigger because they got hotter, and then they cool off. So there's this cycle. And some of them do it in a cyclic manner, and those we call pulsating stars, and some of them do it in this violent manner. And then they get hot, and then they shed their atmosphere, and they get cool, and they wind up down here, where all of the fuel is gone. So the temperature is not high enough to burn the fuel. So part of this process ejects all of the stuff. So we have this wind, and we form a planetary nebula, which ejects the rest of the hydrogen envelope and whatever else in the envelope that might have gotten lost. And we're left with here, we're left with a carbon-oxygen white dwarf. It's made out of carbon and oxygen. The temperature is like 10 to the 8 Kelvin, which is not hot enough to burn carbon and oxygen. It's not hot enough, yeah.
Is the carbon and oxygen both in the core?
Yeah, they're mixed.
So does it wind up hotter than the original star?
Yeah, but not hot enough to burn. Yeah.
Is that just because now the surface is the center, and so that's why it's really hotter?
That's a
Because
no, it's straight up hotter than the core ever was for main sequence star. It's because all of that gravitational energy can't really compress anymore, so it can't release any of the gravitational energy. So it's stuck there, just having that temperature. So it doesn't radiate very much. They're not super bright. That's why they're way the hell down here, because they're not on fire. They just have a temperature, and they're not big. They're very small. So, so what is that? It's held up. What is holding up the star? Degeneracy pressure is holding up the star. This is because you can't have more than 2 electrons in a volume of phase space. So in phase space, remember phase space is, oh, let's make that a vector, is the 6-dimensional space that you get when you consider both your position and your energy. So the position is pretty well defined, it's the middle of the star, and the energy is pretty well defined, it's the velocity of the stuff. So I can't get to, so I have this crushing that's happening from the star itself, trying to push everything into the same spot, but it can't be in the same spot, and it can't have the same energy. So the temperature, which is the energy, and the density is all set by the fact that my electrons all hate each other. And yeah, so this is a pretty stiff pressure. So what can happen from there? So from there, 2 things can happen. It'll stay hot forever. That's not true. It'll cool very, very slowly. So it'll stay hot for a really long time, like the rest of the age of the universe. Or if you could feed it, it'll run into an explosion. So there's 2 ways that we can think about feeding a white dwarf. So remember how I said that all stars are binary stars? So if my star happens to be in a binary companion, I can have a white dwarf, and I can have a main sequence star. So, okay, which one of these has to be more massive? The white dwarf or the main sequence star? Initially, the white dwarf was more massive because it died first. The main sequence star is still burning along on the main sequence. It could be a post-main sequence, like an asymptotic giant branch or a subgiant branch. This could be one of these things that's not quite a white dwarf yet. It's still a main sequence or a giant star. And then I have this cool process called Roche-Lobe overflow, where let's think about the gravitational potential from these two objects. So when I'm close here, my gravitational force is going to be dominated by this guy. And when I'm close here, my gravitational force is going to be dominated by this guy. But if I add them up, I'm going to have some equipotential surfaces where the force cancels out, right? And they look like this. So along this line, the force between the two things more or less cancels out. Okay, it only actually cancels out in a couple of points, but it more or less cancels out. The force is relatively reduced within these lobes. So in this lobe, these are called Roche lobes. These are like the gravitational valley that this guy sits in, and this is the gravitational valley that this guy sits in. So what's this star doing? It's blowing a wind. Why is it blowing a wind? Because it's very hot and getting big and fluffy, and there's all these photons coming off, and the photons come off and they strip off stuff too. So there's a wind from this star that fills up this region of space. And the gravitational potential here is really not very deep, so the gas can just go from this guy over into this guy and spiral onto my my white dwarf. So now a couple of things can happen. So we can have a classical nova. So a classical nova is when, so I've got this white dwarf. And onto this white dwarf, I am piling up stuff. What am I piling up? Hydrogen. So I get this layer of hydrogen. Now, this is really, really dense. These things are only like 10 kilometers or 100 kilometers across. They're really fucking dense. The gravity is really, really strong, so you get this really thin atmosphere of very dense hydrogen. And what does hydrogen like to do when you get it really dense and really hot? Burn. It likes to explode. So you can have nuclear explosions on the surface of this star that spread around the star and blow the surface off, and then leave the star there, because the accretion rate happens fast enough that you can get a bunch of mass on the surface really quick, and then it explodes. This is called a classical nova. These leave the star there. This can happen again and again. There are repeaters that we know about that explode over and over and over again. What kind of a hell is that, to live in a life where you have to explode?
One must imagine Sisyphus happy.
Exactly. Okay, so
can classical novas happen over and over again?
yeah, it can repeat. So you can have the same star that does the same thing a couple of times. Or it can blow up as a type 1A. So a type 1A is the thermonuclear explosion of the white dwarf. So what happens is I fill up stuff, I fill up the star, and it doesn't go fast enough to explode. It just settles and mixes in with the star. And so what does that do? It makes the temperature of the star go up. Why? Because the mass goes up, and I'm putting stuff on the top. So the mass goes up, so the gravity goes up, so the temperature goes up, right? So when the temperature, so then inside, we also have the carbon-oxygen burning rate. So carbon and oxygen burn to neon, say. This happens at a certain rate. And if the energy production rate of this, it's a temperature-dependent rate. So when the temperature goes up, the burning rate goes up too. But the luminosity of the star, that heat can leave too. So if the burning rate gets faster than the rate that heat can leave, then it explodes. Now, we talked about this degeneracy pressure. You will see people tell you that when the star is too massive to overcome, when the star is too massive, the degeneracy pressure isn't large enough to hold the star up, and it explodes. You will hear that explanation too. It is not quite right. The real explanation is about the burning rate. But the degeneracy pressure is sitting there holding things up, and when it starts to burn too fast, then it just blows the whole star apart in a type 1a. So let's talk about what I mean by type 1a. Let's talk about all the supernovae for a second. So supernovae are classified by what's in their spectrum. So the first question is there hydrogen? And if there's hydrogen in the spectra, if there's no hydrogen, then it's a type 1. If there is hydrogen, then it's a type 2. So why would there not be hydrogen in this spectrum? Was that?
It burned it all off.
Or? So it can burn it all off, or what else can it do? What was the other thing that I said the stars do at the end of their life?
Someone else ate it.
Someone else ate it, or it could just get blown off by the wind. So the wind blows it off. Part of the planetary nebula also is an ejection of the upper envelopes of the star. So remember, during this post-main sequence dance, we're left with something that's got carbon and oxygen in the middle, and then a layer of helium, and then a layer of hydrogen. But that hydrogen is pretty tenuously attached, so it gets blown off. So that's like a white dwarf. White dwarf doesn't have any hydrogen anymore. It blew it all off as it was dying.
So it can have a helium-like envelope?
It might have a helium envelope, but it's mostly made out of heavier metals now. So it's mostly carbon and oxygen and silicon. So then we ask, so the first question is there hydrogen? And then there's two questions. So they always draw this like a tree. So hydrogen is the first question. And then silicon or helium. If there's silicon, then it's a type 1a. If there's helium, it's a type 1b. And if there's neither, it's a type 1c. And then the type 2 supernova, these are all type 1 supernova, which have no hydrogen. The type 2 supernova typically get classified by how they decay, and they're either linear, so it's a type 2L, or there's a plateau, and that's a type 2P. What do I mean by that? Let's talk about light curves for a second. So this is the classification. We'll talk about light curves in a second. This is the classification of the supernovae that are out there. That's actually, there's a lot more details here, so there are many, many more kinds of supernova. It's a lot like collecting flowers. You know, every new flower gets its own name. But these are the broad categories. And type 1a, so even though they're classified as type 1 and type 2, this guy is thermonuclear. And all the rest of them are core collapse. Oh, I forgot to talk about business. There are a couple of readings up. I changed the readings. Do the readings now. They're correct the way I want them. There's a stub for the next homework set, which is due next Friday. It's got to be due next Friday. I've been giving everybody extensions because that's how it's been going, and that's been working fine. But there isn't another day after Friday, so you got to get it on time. Sorry, I just realized that I forgot to mention it. We'll talk about core collapse supernova in the next reading. The next reading's is due Sunday, so I'm going to talk about this stuff tomorrow. So the readings are going to lag the lectures a little bit. So anyway, do the reading. We'll read about core collapse supernova. Today we're going to talk about thermonuclear supernova. So the important bit about thermonuclear supernova, I forgot to turn the camera on because or the projector on because one of the most important things about supernova is their light curves. So type 1a are very special because they have this physical rate, and this happens. Okay, so when the burning rate is larger than the conduction time scale, actually, let's call these both time scales. So when the burning time scale, so this is how long does it take to start to burn the material, is faster than the conduction time scale. That's the time scale that it takes to get the heat out. So if it takes a long time for the heat to get out, then the heat builds up and it gets hotter and the nuclear reaction goes faster and then explodes. Make sense? So the burning time scale is set by microphysics. It doesn't care about how big the star is. It only cares about the density. And the conduction time scale also is really set by microphysics because the density and pressure are set by the degeneracy of the gas. And they always do the same thing because it's set by the degeneracy. So there's this very cool mass called the Chandrasekhar mass. Everybody should learn how to spell Chandrasekhar because he's super, super important. The Chandrasekhar mass, which everybody just shortens to Chandra because Chandrasekhar is a lot to write. But the Chandrasekhar mass is 1.44 solar masses, and it's called MCH. This is the mass at which a star will explode. A white dwarf will explode. So if you've got a white dwarf and you're packing mass onto it, they start off as like 0.7 solar masses, and then after 10 million years, then they build up enough mass to cross this point, and then they explode.
So is that just when the pressure from gravity gets strong enough that the CEO to neon burning rate goes up?
It's the temperature goes up. Yeah.
Okay.
But as a result of the pressure.
Yes, yeah.
Yeah. So the pressure, so yes. At the core of that is temperature. So the pressure goes up because of the increasing mass. So there's stuff and it's pushing on you. So the pressure goes up, so the temperature then goes up. And then because the temperature goes up, then you get a nice explosion.
So it's like a threshold mass?
Yeah, it is a threshold mass.
So anything below it, if it feeds, it doesn't explode?
It won't explode until it gets about there.
Oh, it just feeds up to that.
Yeah, it can feed up to there, and once it crosses that point, then they explode. Then it explodes. So this is incredibly useful because this is really specific. This 1.44 solar masses is general and universal and doesn't really care about the rest of the composition of the star. It only cares about about the burning rate, which only cares about carbon and oxygen. So this is really a universal variable. So every type 1a supernova basically looks the same.
So does that mean the luminosity is the same?
The luminosity does the same thing. Well, not the same, but it does something that's very characterizable. So the reason that I put this up is because I'm going to put up some light curves here.
We can account for
So
redshift.
the light curve, so we have this process. So the carbon and oxygen all burn to nickel.
Is that as well as neon, or?
No, nickel is the endpoint. So they start to burn to stuff. It's not just neon. There's all kinds of things that they start to burn to. Once the explosion happens, the energy is so large that all the stuff turns into nickel. A lot of the stuff turns into nickel. So nickel is where the explosion happens. Then I have this big ball of nickel, but it's not stable. It's radioactively unstable nickel. So it decays to cobalt. And that decay is so bright that you can see this thing across the entire universe. there's so much decay from this nickel. Let me pull up.
Is it just all heavier than it's supposed to be?
What's that?
Is the nickel just heavier than it's supposed to be?
It's got too many neutrons.
Okay.
Oh, it's just a
Yeah.
bunch of ours.
Yeah. There is stable nickel. Nickel 57, nickel 50, I forget, nickel 54 is stable and nickel 56 is unstable. I think that's right. I know. Peter
You're
always
gonna be
knows.
right, because that's gonna be on my test in 2 weeks.
I know. Why can I not see my, what the hell? I broke it, guys, I broke the thing.
You broke it?
Broke everything.
Oh no.
Why'd you do that?
I can't get to my other desktop.
So how long does the glow from the decaying nickel usually last?
It's a great question. A few weeks. You can see them as much as many years after, but it takes James Webb. Bear with me 1 second. Why is my display? Oh, because I forgot to. Jesus Christ. There you go. It's just one plot that I want to pull up. It's not really that great, but it's better if I pull up the plot than try to draw it. Here's some good planetary nebula pictures. They're the prettiest things in the universe. I mean, except for you guys. Okay, so you can't really see the white dwarf in the center, but there's a white dwarf in the center. So here's what here's what an explosion looks like. So this is in days. So you can see the maximum here happened at 380. This is Julian day blah. So this is a particular date plus a couple. So the peak of this explosion happened at 380. What happens before the peak of the explosion? Before the peak of the explosion, there's this thick shell of carbon and oxygen that hasn't burned yet, that the explosion is working its way through. So the explosion starts to work its way through the supernova, and then it's got to lift all of that material that it just blew up away from the star. And then once that gets thin enough, then you can see the actual explosion. And then the nickel decays, and the explosion gets dimmer and dimmer and dimmer and dimmer and dimmer over the course of a couple of years. So this is 80 days, which is several months. But they keep going. They're still there for many years afterwards. So now, what makes these awesome is do I have? Oh man, I don't have the other plot. So this is actually a family of supernova that we stretch to all get the right to be on the same time scale. So there's this relationship called the Phillips relation. And what that says is, if you look at how fast it's going down, so this is how much dimmer it is after 15 days. That's just a rate of change over a time, and we pick 15 days as the fiducial time window to get our derivative. But it's really just a derivative, is the slope of this line tells you the peak brightness of the line. So
is that any 15-day period, or is it from the peak?
From the peak. So it's the 15-day period from the peak. So how dim is it after 15 days? That tells you the peak brightness in this relationship here. And this isn't, I'm going to write this on the board over here, because I don't know if it's in the book in a nice, clear way. So write this down. Is minus 21.7 plus 2.7 delta M 15. And this is the this is the brightness, delta M15 is the B band, the apparent B band magnitude at t equals 0 minus the apparent B band magnitude at day 15. This is about the apparent magnitude. And that's why this is powerful, because the apparent magnitude is giving me the absolute magnitude. And remember, apparent magnitude and absolute magnitude are vastly different quantities. So I got this thing that gives me the absolute magnitude from the apparent magnitude. What can I do with it? If I
You
can
get
the what? You can get the distance modulus, and thus the distance of the star. And what did I say about these things? They're so bright that you can see them where?
everywhere.
Across the entire goddamn universe. So you can measure distances across the entire universe now with these things, which is really fantastic, as long as they're calibrated correctly. And now we've recently run into a problem where the calibration is off, and if you ask for the age of the universe one way, you get a slightly different answer.
So is the negative 21.7 like the maximum brightness that it can get, like the explosion gets?
I don't know. This is just a linear fit to. I mean, delta M15 is never going to be 0, so it's always going to decay some.
Is that the thing where the star was like more than 13.8 billion light years away, or something?
There are several. So we can see things that are a little bit more further out than that because of the expansion history.
I thought it was like a lot further.
Sometimes those show up. So I'm not sure which thing you mean. So
I don't know.
it's possible that it's just the universe is actually not 13 billion. Like you can have something that's a little further away than that just because of the history of the expansion. You got to do an integral, and there's an extra factor of 1.5 that shows up. But there are also measurements that people have done. So globular clusters were thought to for a long time. It was believed that globular clusters were older than the age of the universe because the age of the universe measurements were wrong. Because if you don't include the dark energy, you don't get the right age of the universe.
Oh, like with the Hubble
Yeah, with the Hubble constant,
Yeah.
that's right. Do you have a question?
So like when it's supernovaing, how long is it actually exploding for?
The actual explosion rips through the star in a half a sound crossing time of the star, which is a couple of seconds.
Oh, okay.
So the whole thing gets totally undone in a fraction of a second. And then you're left with this hot ball of stuff that is getting bigger and bigger and bigger, but it's not exploding anymore. But it's still burning, so it's still on fire. So there's still nuclear burning that's still driving this expansion. So the star is gone kind of right away, but then there's this thing that's kind of still exploding, if that makes any sense. There's this fireball that's left behind for after
So
the
it's
star
like you
is
have an
gone.
explosion, and then after the explosion, everything's still on fire
Everything's still exploding.
and exploding.
Yeah,
Oh.
it's like if you have a fire in a fireworks factory.
And
Like-
it reaches peak brightness after like the initial explosion.
Yes, the initial explosion happens, and then it's shrouded by this thick stuff. So it's not until it expands enough that you can see through the stuff that's when you get the peak.
And
how do we know when the peak is? We just watch it from the start to the end?
Yeah, you got to catch it before and after, and then you can figure it out.
so, just to help me understand,
Yeah.
the big MB is the absolute brightness at 15 days?
That's the absolute brightness at the peak.
Oh, it's at the peak.
Good question.
And that's B-band brightness?
Yeah. And then this is apparent at t equals 0 and apparent at t equals 15.
And T equals 0 is the peak.
T equals 0 is the peak. Yeah, that's right. Actually, yeah.
Is that right that it's initial minus final?
Yes.
T0 minus
No, it's
T-
final minus initial.
So it should be MB15 minus MB0?
Yeah, I wrote that backwards.
Okay.
That's not on this slide anywhere. That's what I get for talking while I'm writing at the same time. Okay. That's M15, and I got 5 minutes left. Okay, cool. Let's see. Then we can get distances. Okay, so let me talk real quick about, because I got 5 minutes, which isn't really long enough to do anything real. Since I've said everything I wanted to say about. But let's talk about the Hubble tension real quick. So I don't have slides prepared, so I got to pull up my plot, the plot that I want from the internet. Here we go. So here is one of the most fascinating things, and this is developed. So you can't really. So this is year of publication and the Hubble constant, which is the expansion rate of the universe, which we haven't really gone into. We'll go into in detail in XGAL, but H naught is the expansion rate of the universe, and it is 70 kilometers per second per megaparsec. So if you're a megaparsec away, that thing is accelerating away, is moving away from you at 70 kilometers a second. 2 megaparsecs away, it's accelerating away from us at 140 megaparsecs. So there's this question of whether or not the value is 72 or 68. And if you measure the expansion from the cosmic microwave background, which is the light from the Big Bang and is really deeply tied to the state of the universe, because the universe was homogeneous at the CMB, or thereabouts, mostly homogeneous. So this is a very sensitive probe of the initial state of the universe. Whereas if I use supernova, I get 72. So I get this slight difference. And you can see when I started, let's see, I got here, here. I came to FSU here. So as I've been here, the error bars on both the CMB measurements and the supernova measurements have been getting smaller, and they're getting further away. And then there's this also, remember we talked about the tip of the red giant branch. So there's this point where the red giant branch has a helium flash and races away. And everything's at the same brightness at that point. So that's a very good way to measure distances too. And that gives us a value that's in between the two. So this is one of the most interesting open questions in astronomy right now, is what the hell is going on, because we thought we knew how the universe was expanding, and then we measure it twice and we get 2 slightly different answers. And get repeated measurements doesn't make that better. So it's hard to say what's going on. So supernova actually measure the rate of the expansion, because we measure that supernova, we also measure its velocity. So we have its distance and its velocity very well. So the only trick is we have to calibrate this relationship. This relationship is empirical. So we have to calibrate it with this distance ladder that I haven't talked about yet. Yeah.
Why would the cosmic microwave background be more accurate?
That is a great question. I don't know which one is more accurate.
Okay.
Because one of them is measuring the actual expansion. Measuring it with supernova, you're measuring the velocity of the stuff. So we're actually measuring the expansion. Whereas when you measure it from the CMB, what you measure is the ratio of peaks. You measure the shape of the acoustic disturbances. So you measure how many acoustic disturbances of what size you get. So it's a little bit less direct of a probe of the expansion rate. But it's a simpler system because there's not as many systematics to work out. So we have to understand Cepheid variable stars and supernova really well to make this measurement work. We probably don't understand Cepheids or supernova very well, but because they're both hairy systems, they're both messy systems that have a lot of little details. Yeah.
Isn't the Hubble constant supposed to get lower and lower over time?
No, it's supposed to be constant.
Well, yeah, I know it's called constant. Yeah, but like, isn't it? I don't know exactly what I'm trying to ask.
Okay.
I'll figure it out.
No worries. Well, I'll be around. Yeah. So that's. But that's. No, it's all right. So like, how many of these constants are constant? Like, that's an interesting question. Is the speed of light actually constant? Because if it's not, there's problems. And there's a conspiracy theory called tired light that says that the speed of light is just getting smaller. We've measured it. It's not. But yeah.
So why do they start at the same? All start at roughly the same spot.
Here?
But and then they start about the same. Like the dots at the same spot, more or less.
Yeah.
Although the tip of the red giant is a bit smaller. And what happened? Why did they end up splintering off?
This goes from here to here because of the Planck satellite. So once the Planck satellite finished its mission, then we had a really incredible map of the CMB. And so that's how this got small, because that happened in that's this jump. When it goes from here to here, this is Planck coming out. So this is Kobe. So that was a balloon experiment that wasn't very accurate. This jump here is WMAP, which is another satellite, and then this one is the Planck satellite. So successive satellite missions have improved that measurement significantly.
Okay.
They all started around 100 because that's what Hubble back in the 20s. I can't say the 20s anymore. We're in the 20s. Back in the last 20s, Hubble wrote down 100. So we all started from 100, which isn't quite right. So.
And the Cepheids, those are the supernovae and stuff?
Yes, a Cepheid variable is a variable star, and those are used to calibrate the supernova. So really this should be Cepheids plus supernova.
Okay.
But the Cepheids are the main source of uncertainty, which I didn't talk about Cepheids. I probably should, yeah.
Question about that.
Yeah.
I know Cepheids can exist outside of the red giant branch. But the one inside the red giant branch, you said like it's like unstable and it'll fluctuate. Can you use those as a Cepheid variable star also?
Anything that pulsates is useful.
Okay.
So then there's a whole bunch of classes. There's a whole bunch of different classes of pulsating stars, which I really should spend a minute talking about pulsating stars, but I don't want to actually assign the whole chapter because we're running out of time. So the readings that are left are late stage stellar evolution, which was due today, massive stars, which is due Sunday, and then star formation, which I'll cover next week. And I'm covering that because that's my favorite stuff.
It's not thermodynamics?
What's that?
It's not thermo?
No, it's all related. I like thermodynamics and star formation. They're all embedded.
Seriously, you were talking about that we had two topics that we had tried. It was like cosmology and something else.
Oh yeah, there were so many things that I wanted to get to.
We're not getting to that. What was the other topic going to be?
I think it was either cosmology or galaxies, but it might have been planets because I wanted to talk about planets too.
I know one of them was cosmology, but I don't know.
I think
what
one
the
of them
other
was planets.
One of them was certainly planets.
I only remember cosmology because I was like, oh, if we have a vote over that.